we're going to start today into our last section of chapter 10. And so what you can look for is that we are going to have a unit quiz. You'll get more instructions as we go on in terms of what that looks like. And then the homework tonight will be starting into a review. So it's not just 10.3 directly, 10.3 day 2, but it will go into more of a review from the unit so that we can bring everything together so that we'll have some sort of final assessment that you'll get more instructions as we go. So as we get started here, I know that it's been a while since spring break, and I know some of you might have put this long behind you. So we're going to start with a warm up into some geometric series problems, and then we're going to go into our application. So it should be pretty short today. So first problem, it says a geometric series has a first term of 34 and a common ratio of 1.7. Here's what that means for us. The first term is always A1, so A1 has a value of 34. And then the common ratio we call R. So that means R is equal to 1.7. It asks us to find the 20th term. So that's A sub 20. And then the 20th partial sum, which is capital S sub 20 for our sums. So for a geometric series, as a reminder, and these are all formulas that you would get for your assessment. So it's the nth term, AN, is the first term times your ratio to the n minus 1 power. So let's see here. If we're looking for A20, that means that A20 is equal to A1, 34, times 1.7 to the n minus 1. Well, n is the term number they're asking for, so n is that 20, so it's 20 minus 1, or 19. So now is that point where we would go to our calculator, and then make sure that we follow order of operations. So it's 34 times 1.7 raised to the 19 power. You don't want to do 34 times 1.7 first, otherwise that will mess up your answer. All right, we get a big value, so that comes out to make the 20th term 812,846. Let's do 3 decimal places, 0.281. So that's 812,846.281. So something to pay attention to here real quick is that we started with 34. 20 terms later, we are at 812,000. So that grew very fast, even though the ratio was pretty small. Keep that in mind. That's an exponential growth thing, which we're actually seeing right now happening. All right, so that's the first one. Then it asks us for the 20th partial sum. For our 20th partial sum for a geometric series, as a reminder, Sn is equal to the first term times 1 minus your ratio to the n power over 1 minus your ratio of r. So, close this. S sub 20 is equal to the first term, 34, times 1 minus 1.7 to the 20th power, get this out of the way, to the 20th power over 1 minus 1.7, all in parentheses. So then now, for this, when you go to your calculator, you just want to be careful. It's easy to miss a parentheses. I'll show you how I write it all in one line. You can also split it up if you don't feel comfortable with that. The big thing is parentheses. So it's 34 times. Now I'm going to put my numerator in parentheses. 1 minus 1.7 raised to the 20th power. And then come out of that, close your parentheses. So that's the numerator divided by. Now I want to put the denominator in parentheses. 1 minus 1.7, close it. So that's grouped together. Click enter, and that gives us a sum of 1,000, what is that? Oh, I think that is 1 million. There we go, 1,974,006.683. Massive sum. So that is our sum. All right, next up, let's look at an example where they don't tell us the ratio. A geometric series has a first term of 12. So that means A1 is equal to 12, a 10th term of 120, so term A10 is equal to 120. Whenever possible, I always try to go back to my formula for each term. Remember, that's an is equal to a1 times r to the n minus 1 power. So for our case, we're going to use n as 10. So that means that a10 is 120. We have a number for that. That's equal to 12. We don't know r. And then n was 20, or sorry, n is 10, the 10th term. So to the 10 minus 1 power, or to the 9th power. So what I can do here is now I have to solve for r. Undoing order of operations, I would start and get rid of the 12 in front. So divide by 12. And that gives us 10 is equal to r to the 9th power. And so then to get rid of that, I am going to raise this to the 1/9 power or take the 9th root, either way. So that makes my r equal to 10 to the 1/9 power. Or if you prefer it, you could write this as the 9th root of 10. Those are equal. All right, cool. That wasn't that bad. You could get a decimal approximation for this. We're going to keep it exact and not do that. So next up, 12,000 is a term in the series. It's somewhere. This means that we don't know what n is. What is the term number? That's n. So n equals 1. So that's some an term. So this means for us here, we're going to say, all right, 12,000 is equal to my starting value of 12 times 10 to the 1/9 to the n minus 1 power. Let me break that down again. Wherever an goes, that's some term later on in the sequence. I put that here. 12 is my starting, 10 to the 1/9 power is my rate, and then this is the n minus 1, and n is what we're looking for. So just like we did before, I'm going to divide by 12, and 1200 divided by 12 is 100. So that means 100 is equal to, and now I'm going to do a little bit of rearranging. When you raise a power to a power, they multiply. So this becomes 10 to the power of 1/9 times n minus 1. I know it's a little small there, so oops. 1/9, oh my goodness, I did it again. There we go, 1/9 to the n minus 1 power. And give me just a second, it's glitching here. I'll try to cut this out later. Okay, there we go. Now I can type 1/9 to the n minus 1 power. Okay, here's what we got. This is a whole case of going back to our last unit on exponentials and logs. I have my variable n stuck in the exponent, and the only two options are to write my bases as write these sides as some same common base to the same power or to different powers, or take the log. Well, thankfully 100 is a power of 10. So I can rewrite this as 10 to the 2nd power equals 10 to the 1/9 times n minus 1 power. Now that I have bases of 10, remember that we can ignore them and set equal and make this 2 is equal to 1/9 times n minus 1. This gives us, now at this point I would multiply by 9. So multiply by 9, that gives us 18 is equal to n minus 1. Then add 1, that makes n equal to 19. So that means that the 19th term in this series is going to be 1200. All right, now, so let's get into our notes for today. We're not going to do anything new, but what we're going to do is we're going to look at a couple of real world contexts and interpret them through the lens of sequences and series and determine if they are arithmetic or geometric. So the big idea here is if it is arithmetic, we're going to be adding or subtracting by a common number each time. If the situation is modeled by a geometric sequence or series, we are going to be multiplying or dividing to get to our next value in our list or in our situation. So here's our first one. Assume we take a job that pays $30,000 a year, and that's a very small highlighter. Here we go. $30,000 a year, and you earn a 4% raise each year for the next 39 years. What is your total compensation for the entire year? So there's two different ways that raises go. There can be a fixed raise where they say we're going to give you an extra $1,000 each year, and so each year they would add 1,000. Or to figure out what 4% is, we're going to have to multiply in order to figure out what that value is as it increases. So as we do this, if I want to take 100% of my salary and increase it, we're going to be multiplying. And the rate that we're doing that will be a rate of 1.04, because what this does is it takes 100%, it adds on 4%. That means that 104% is 1.04. And that's really important here. Okay, so this is going to be a geometric situation because we're multiplying by 1.04 to get to my next value as we go. And so then now, since it says what is my total compensation for the entire 40-year period, it wants to know what the sum of my yearly salaries was. So you have two options. You can just figure out what your salary was at 40 years, or we can add them up, and that's what this situation is asking for. So it wants us to take the 40th partial sum. So I'm going to use the formula. If it's still unfamiliar, go back and look it up. So it's the first term, which is 30,000, times 1 minus your rate to the n power. So 1 minus 1.04 to the 40th power over 1 minus 1.04. So now let's go and put this in the calculator. Okay. What I'm going to do is I'm going to multiply by 30,000 last, just because that's a large number. So it's 1 minus 1.04 raised to the 40th power, close those parentheses, divide by 1 minus 1.04, close your parentheses, multiply by 30,000. Make sure you grab all the zeros. And that gives us a total compensation of 2850765.47. Let's round to two decimal places because it's money. Let's add our place values in there. That looks like $2,850,765.47 over 40 years. Think to yourself, is that a lot of money together? Maybe it's not. Maybe you've never thought about what it looks like to calculate a salary over 40 years, but that's what the total amount would come out to. All right, that's situation one. It was geometric. Let's look at a couple more. Assume that whenever you wash a pair of blue jeans, they lose 4% of their color that they had just had before they were washed. The percent of the original color left in the blue jeans varies geometrically with the number of washings. What is the common ratio? All right, so that was nice of them. They told us it was geometric. So now they want us to know what this common ratio is and it says of the color left in the blue jeans. So what I want to think about here is if I assume that I have 100% of my color, I take away 4%. What percent is left of the color? Well, that would be 96%. The easiest way to then we figure out a percentage, your common ratio will just be that percent turned into a decimal, which we move the decimal place back to. It makes our common ratio 0.96. All right, so now we're going to use that. All right, so now that we figured out our rate of 0.96, we're going to go and we're going to figure out, part B, how much of the original color would be left after 10 washings. So for this problem, what we want to think about is this is going to be our term A10. So what we want to think about is how many times we are multiplying it by this 0.96. So for 10 washings, that's going to be the 10th time would be 100% of the color. We need some starting value. We're going to say we start at 100%. They have full color times 0.96. Now here is an exception. Usually it's to the n minus 1 power, but this time we want every washing to count. So the first time we wash them would be n equals 1. So we want it to be raised to the first power. So we are going to make this an exponent of 10 rather than 9 for n minus 1. So going over to the calculator, this would give us 100 times 0.96 raised to the 10th power, which is 66.5% of the original color. So that's pretty drastic. Depending on if we like that or not, that would be what they're predicting the effect to happen. So then they're switching the scenario on us around a little bit in part C. Suppose we buy a new pair of blue jeans. We decide to wash them enough times so that only 25% of the color remains. How many times must we wash them? So in this case, we would want, if we want the percentage to be 25, we want 25 to equal 100% times 0.96, and then we're going to say raised to some power, and we can make that n here. We want to know how many times we have to wash them. All right, so then we're going to solve this by hand now. So at this point, let's start and let's go ahead and divide by 100. I'm going to move this over. And I'm going to go ahead and turn it into a decimal. That makes this 0.25 is equal to 0.96 raised to the n power. Now remember, two ways to get an variable out of an exponent is we either can get them as a common base, which is not possible here, or we take the log of both sides. So I'm going to take the ln of both sides. So that means the ln of 0.25 is equal to the ln of 0.96 to the n power. Next up, we popcorn that n out front, so that means the ln of 0.25 is equal to n times the ln of 0.96. Remember that that's just a number, and so now I'm going to divide by the ln of 0.96. And so that means here that my number of washings is equal to the ln of 0.25 divided by the ln of 0.96. So let's see what that is. You could have used the log again. It doesn't make a difference as long as you're consistent. So the ln of 0.25, close parentheses, divided by the ln of 0.96 is 33.95. And we'll say that has to be 34, we'll round it up, 34 washes to get 25% of the color. All right. So far you might be thinking, every situation we've seen is geometric. When does an arithmetic situation show up? And this last example here that we're going to see is going to be an example of one of those. So here's what we have. We have two people take a walk, which hopefully you are getting out and taking lots of walks right now. It's gorgeous outside and it's good for our health. Jack and Jill start walking at the same time from the same point in the same direction. Jack starts with 12-inch steps and he increases his stride by half-inch step each time. So 12 inches at the start, he increases by half an inch each step. He goes 21 steps and then stops. Jill starts with a 36-inch step, so a bigger step, and then each subsequent step is 90% as long as the previous one. Do Jack's steps follow an arithmetic or geometric sequence? So for Jack, he is adding the same amount each time, so that makes it arithmetic. For Jill, because each step is some percentage, that's a multiplier. And so that would make her situation geometric. So we get to compare and contrast how these two methods work here. So it says, how long is Jack's last step? Well, he took 21 steps. So his last step will be however long the 21st step is. So that's going to be for Jack, step term A21. So for a arithmetic sequence, we take the first term, which is 12, plus our common difference, so what we're adding each time, which in this case is 1/2, times n minus 1. So that's times 21 minus 1. 21 minus 1 is 20, and half of 20 is 10, so that means it's 12. His last step length is 12 plus 10, which is going to be 22 inches long. So his last step is 22 inches long. For comparisons, let's figure out Jill's 21st step. So for Jill, we've done this one some today, so hopefully it feels a little bit more familiar. For a geometric sequence, the 21st term, we can find it by taking the first term. She took a 36-inch step times the common ratio. Remember, we have to turn it into a decimal, so that's 0.9%, and then times n minus 1. So that would be to the 20th power. All right. So here we go. So this would be 36 times 0.9 raised to the 20th power, which makes her last step, let's do 3 decimal places, 4.377 inches long. So her steps are getting significantly smaller at this point, while Jack's are getting bigger. All right, so now that we know how long their 21st step was for each of them, we are going to make a comparison. After each has taken 21 steps, who is ahead? This means that we want to add up the different lengths of their steps. They're changing, but we want to add the total up and see each step, how far is their total distance. So this is going to be our sum formula. So for Jack, since he's an arithmetic series now, I want you to remember that the nth partial sum, this will be the 21st, is n over 2 times the first term, a1, plus the last term, an. So for this case, the 21st term is 21 over 2 times the first term was 12 inches. The first step was 12 inches long, and his last step was 22. And so then that's going to give us, I'll probably do some of this in our head, but here we are, 12 plus 22 times 21 divided by 2. That makes his total amount of steps 327 inches long. So now we're going to see if Jill went the same distance, how it compared, because she did start with a 36-inch step. So that's a pretty long step. So I'm curious to see what happens. So for Jill, the sum is going to be the first term. So the sum of the 21 terms will be the first term, which is 36, times 1 minus r, which is 0.9, to the 21 power over 1 minus 0.9. So now, that makes this 36 times 1 minus 0.9 raised to the 21st power divided by 1 minus 0.9, which makes it close but not quite 320.609 inches in total. All right, so let's step back and compare these. All right, so who went farther? Jack definitely is the winner, and he went further with this method here. Now, here's the interesting thing. Jack stopped after 21 steps. If Jill kept this pattern going, what you want to think about is that her steps are going to get smaller and smaller and smaller and smaller, but despite human error, she could keep going at these, she could keep taking 90% of her inches and take smaller and smaller steps, but eventually the difference is going to be negligible. She's barely going to move at all, and so we can get the infinite sum of this because the rate is less than 1. So remember that our r is equal to 0.90, so we can take the infinite sum, remember that it's the first term over 1 minus r. So the question says, if Jill keeps walking on forever in the same manner, will she ever get to where Jack stopped? Let's see. First term, she took 36 inches the first time, times 1 minus 0.9. You could just put that right into the calculator, or you can make this 36 divided by 0.1, and 36 divided by 0.1 is 360 inches. So did she make it? Yes, she made it. It would take a long time if you did it infinitely, but she would make it to 360 inches. Awesome. Okay, so that is the end of applications. Hopefully what you saw here was an awesome review. There was nothing new, but the biggest thing is when it's a word problem scenario, it's harder to piece apart. Are we multiplying? Are we adding? So a couple of hints is when you see percentages will most of the time come out to be geometric because we multiply our values by percents as we work forward. All right, so tonight's homework is going to be review, and that will lead us into a summative quiz, and you'll get more details on that in the days to come. That is it. Let me know if you have questions. Come to office hours if you need help.